the Laplace transform of h of t. Now this function is defined on the document. It's the Heaviside function. It's equal to 0 up to t equals 0 and thereafter equal to 1. This is 170425. Okay. So in this document, that function is defined. The Laplace transform, of course, is the integral from 0 to infinity of e to the negative st times that function. Now, between 0 and infinity, that function has a value of 1 by its definition. So its Laplace transform is just this integral, and the integral is totally straightforward, and you get 1 over s. So you'll need to fill in the details to convince yourself that that's the case. Now remember last time we found that the Laplace transform of the function f of t equals t was 1 over s squared. And the Laplace transform of t squared was 2 over s cubed. There's a series of reciprocal s powers, and you see those in your table. So we talked about where that comes from last time, and there's an inductive proof of what I just said about the higher powers. Okay. Heaviside function applied to t minus alpha. Now, what's Heaviside function of t minus alpha? Well, you need to understand that this is just the Heaviside function horizontally shifted alpha units. Now you might then ask yourself, well, what's the Laplace transform of the Heaviside function of t minus alpha? Okay, well then, integral, the Heaviside function would be 0 up to alpha, and then it would be 1 thereafter. So you'd have the integral from alpha to infinity of e to the negative st times 1. Because the integral up to alpha, you're multiplying by the Heaviside function h of t minus alpha, which is 0. So you should be able to work that out rather easily. Now, why is the Heaviside function important? Well, a very important class of functions is square wave functions in applications. It's where you exert a constant force for a while, then you exert the opposite constant force for a while, then you switch back to the constant force, then the opposite at regular intervals. Or you apply a voltage to a circuit, and then you reverse the voltage. Then apply the voltage, apply the reverse voltage, and keep doing that and see how the circuit responds. You can build up that kind of square wave function from Heaviside function, okay? And we just consider h of t minus alpha. Now this isn't on the document. I'm adding this in as an explanation of why you want to use the Heaviside function, why it's important. And we're not going to work through all the details of this. Now you should be able to graphically add the Heaviside function, which is this one. This is your h of t function, and this is your negative h of t minus alpha function. Just the opposite of your h of t minus alpha function. Now this is implicitly 1 here, negative 1 here. I didn't keep the scales all that constant, but that's the meaning here. So up here the Heaviside function is 1, down here the Heaviside function is negative 1. So what happens if we add the h of t and the negative h of t minus alpha function? Well, up to 0, both functions are 0, so when you add them, you're going to get 0. So everything up to t equals 0 is going to give you 0. Now, you cross t equals 0, and now the Heaviside function is 1, and the negative shifted function is still 0. So that the values of the sum of these two functions is just going to be this function up to the point where this one is no longer 0. So you're going to get this. Now, when this one suddenly changes to where its value is negative 1, well, that meshes up with the value of 1 here and gives you 0, so from here on to infinity, you get 0. You need to be able to see that algebraically and graphically without punching it into a calculator. You need to be able to construct the sum of two simple functions like this. And then you can think of how you might go about getting a function that just keeps switching back and forth. what combination of Heaviside functions would accomplish that. There's a sequence and a repeatable sequence, or at least a recursively defined sequence of Heaviside functions that would do this. Now, there are other things that we'll do. Once you get one period of the Heaviside function, you can extend that using something that we'll develop within the next couple of classes. Okay, so that's it. Now, we move on to computing Laplace transforms of a couple of other functions.